Hey guys, welcome back. Welcome to week 2 of our e-learning of acids and bases. I'm going to start off today with a little bit of my notes over the Arrhenius definitions of acids and bases. But before we get into that, make sure you've done the reading that was linked in Classroom. This CK12 website is basically an online textbook to help give us the background that we need to go with the videos. So I want you to watch the video. I'm sorry, do the reading when there are embedded videos like this one. Watch it. You don't have to take notes, but pay attention because in the end, it's going to ask you to do a little bit of practice. You can see here down at the bottom where it says view practice. You're going to be asked to basically get 10 questions right. It's low pressure. You can retry the questions. There's no time limit. But it's a lot easier and a lot more productive if you're paying attention to the reading and the video so that you can answer those correctly. So please make sure you've done that already, and then I'm going to get into my notes. Okay, so an Arrhenius acid is a compound that reacts with water to produce hydronium, H3O+. And the example that they use in the reading is HCl. So HCl reacts with water and it produces hydronium and it produces, in this case, Cl minus. Okay, so first of all, what's happening here? Well, basically, if you look at HCl, HCl is just a hydrogen sharing 2 electrons with a chlorine. And this chlorine has 6 more electrons, 3 more, unshared pairs of electrons hanging out there. But what happens is the hydrogen itself, not the electrons, but just the positive hydrogen nucleus. Because remember, hydrogen has the atomic number 1. It's just its nucleus is just a proton, a single proton. And so what's happening is that single proton is being taken and added to a water molecule. So water would look like this. This is its Lewis structure. And essentially that single positive proton is going to grab on to one of these lone pairs and it's going to create this hydronium. So it's going to be H bonded to O, and water, which was H2O, is now H3O. And because it just took the positive proton, it was just the positive proton, this hydrogen atom here, it didn't take any electrons with it, that now gives what was a neutral water molecule a positive 1 charge. And so hydronium, as you can see up above, has that +1 charge. And it would leave behind a chlorine, and actually it's called chloride now because it's got all 8 electrons. If we go back, and so it has a -1 charge. And so if we go back over here, you can see it kept both of those 2 electrons in that bond, which means it has 8, which is 1 more valence electron than it started with. If you look at a periodic table, chlorine only has 7 to start with. Now it has 8, so that's why it has a -1 charge. So we have hydronium and we have chloride, and that's what we call an ionization equation. So either one of these two you can label as an ionization reaction or equation. Okay, and that's what makes HCl an acid, the fact that it's able to react with water to produce hydronium. Now the reading gets a little bit fancier and goes into talking about why some things do this and other things don't. I'm not super concerned that you know that. Basically, it's just telling you that this bond between hydrogen and chlorine is broken pretty easily because it's a very polar bond. And that simply means that the chlorine has a more positive nucleus and is pulling on these 2 electrons, pulling them closer to it than those electrons are to the hydrogen. And it makes the hydrogen very likely to sort of slip away and go attached to a water molecule. Don't really have to know that, but if you're curious, okay, how come not everything that has hydrogen in it is an acid? That's why. It has to do with that bond being polar, which is not something that we spend a whole lot of time on, but that's the reason for that explanation. Okay, just so you have seen it and seen a little bit more of these ionization equations, let's take a look at another one. So if we had, let's say, HF, and we had some water, what would that ionization look like? Well, first of all, you would have to know that this is an acid. It's an Arrhenius acid. And we can tell that because it has this hydrogen out in front. And what's going to happen is the hydrogen is going to get attached to the water just like it did up here. It's going to be lost, away from the fluorine and added to the water. So what's that going to result in? Well, it's going to give us H3O plus, and then in this case, it's going to give us F minus. And again, the reason that this is positive and this is negative, whereas these guys didn't have any charges, is because it's just the hydrogen proton, which is positive, that is getting transferred from the neutral HF. And if something is neutral, meaning it has zero charge, and then you subtract a positive one particle from it, it becomes negative, and that's why you see the negative sign on the fluoride. If water is neutral and you add a +1 proton to it, it's now going to be a +1 charge, and so that's why you see the charge on the hydronium. Okay, so hopefully at this point you feel like you could write your own ionization equation. Basically, it's just giving the hydrogen from the acid to the water, making hydronium, and then a negative ion. So the other term that gets introduced in this reading is the concept of monoprotic acids versus polyprotic acids. And all that means is if you break down prefixes and roots, it simply means, well, mono means one, right? So an acid that has one hydrogen proton would be a monoprotic acid, just like HF. So HF would be an example of monoprotic. I'm just going to say mono. Now there are some acids that have multiple hydrogens, and so they're going to be like H2S, for example. This one it would be called polyprotic because it has multiple hydrogens, multiple protons. Remember, a hydrogen is just a proton. So this is polyprotic. And actually, if we want to get really fancy, so polyprotic, we can actually specifically say how many hydrogens it has. And so it's H2S, it has two hydrogens. And if you remember the Greek prefix for two, it's di, right? So this is specifically a diprotic acid. There are even triprotic acids. This is about as big as it gets, like H3PO4. It looks complicated, but the main thing is it has three hydrogens. So this is a polyprotic also, but specifically it is triprotic. Now, when you write ionization equations for these diprotic and triprotic acids, it's not as different as you might think. It's actually pretty simple. If I were to write an ionization equation for H3PO4, it's still just going to be one hydrogen that gets lost from that acid, that H3PO4 acid. And by the way, if you remember all the way back to last week when we talked about naming, if PO4 is called phosphate, what would H3PO4 be? What acid name would that get? So hopefully you remember 8 becomes ic, so this is phosphoric acid. But anyway, when it ionizes, yes, it has 3 hydrogens, but it doesn't lose all 3, or at least not all at once. It just loses one of them. So one of those 3 hydrogens is going to jump from here to here, creating a single hydronium. But then what would you be left with? You're going to go from H3PO4 2H2PO4 with a -1 charge. Well, you say, well, why does it have a -1 charge? Well, if it had 0 charge to begin with and we lose a positive proton, it's now going to have a -1 charge. Okay, guys, so that is our discussion of Arrhenius acids. We are going to go ahead and this is an ed puzzle, but I've only made it an ed puzzle for the purpose of making sure that you've watched it. Hopefully you've taken the notes, but I'm not going to be checking that. But you will be able to use those notes to do the next phase, which is going to be a Google form sort of little homework open note quiz. So please go there next, or you can rewatch this video if it helps you at all. Um, and then we're going to have another lesson on Arrhenius bases.